Hi, my name is Tanner Williams, and I'm partnered with Axel Maberry working on a Python code that will provide the exact solution for transient conduction problems. In transient conduction, there are two different assumptions that are given in heat transfer, namely one term and lump capacitance. Our code gives us the exact solution, and we are understanding what the error is for these assumptions and why are they accepted in the professional world. With the exact solution, we have three different geometries in consideration: plane wall, spherical, and cylindrical. With each of those, we need to understand the Biot number related to the problem. With that Biot number, we find the roots of the zeta equation. Then we solve for the C values, and then we put those into the multi-term summation equation to calculate for either Fourier's number or the final temperature on whichever we choose. And then we keep adding terms until our error is within an acceptable amount. The code needed to be able to find the roots of the different types of problems according to the Biot number. The zetas of each term are where the Biot number crosses with the zeta equation. So as you can see there on the 3, the Biot number crosses at different points according to the three different geometries. To keep our code nice, we solved each of those for 0, adding Biot number into the equation, shoving it down to 0, keeping the zetas on the zeta axis. That way we were always solving for 0 and keeping our code simple. Using Ritter's method made it easier for us to find the different zetas for the multi-term equation. Because our tangential-like equations have many asymptotes, we had to make sure that we didn't find the roots when it went from positive to negative infinity, as Python can. So we set the boundary conditions at where Biot would normally be 0 and at the asymptote. So the root was always between those values. So for our first zeta, it was between the two red dashed lines, and then we moved on to the next one as shown in the green. The right hand one was always the next asymptote to help keep it away from converging on the asymptote.
Once the zeta value has been found, we need to also solve for the C value per iteration. The equation for said C value changes with each geometry. Once we have that C value and zeta value, we are then able to solve for either our final temperature or our Fourier number, which will give us a time, depending on the user input into the code. As this is a summation equation, we are able to continually add terms until the error is in an acceptable region. Testing the code resulted that exact solutions were given when either solving for time through Fourier's number or the final temperature. The inputs to this code include the geometries that you would like to solve for: the heat transfer coefficient, the corrected length factor, the atmospheric temperature, and the initial temperature. You are then asked whether you want to solve for the final temperature or the final time. After that, you're able to input the properties of the material that you are working with. If iterations are needed, additional prompts will be asked for more information. Finally, either final time or final temperature will be given. As you can see here, putting in these values, we are able to see that it works both ways given a final time or final temperature. The exact solution should be compared to the approximate solutions to see the relative error. Using Biot number of under 0.1, we're able to compare with both lumped capacitance and one-term solutions. Using this, we see that the time needed to solve for these certain temperature ranges varies, but only slightly, with relatively small error of about 6 and 11%. Additionally, when dealing with BO numbers greater than 0.1 and Fourier numbers greater than 0.2, a one-term approximation is an acceptable solution. As we can see when compared to the exact solution, we have visible error near the beginning of the chart. But as time progresses, it becomes hard to differentiate between the exact and one-term solutions. Using the time it took to reach the final temperature, we're able to see that we do have negligible error between these two solutions.
As these previous assumptions do not cover all the problem types, we needed to use the exact solution to solve for Fourier numbers less than 0.2. The code was able to then give us the number of iterations needed to reach an error in our final temperature of less than 1 times e to the negative ninth. We gave them all the same constants to keep it the same, with an initial temperature of 10, a T infinity of 100, and with a Biot number of 0.3. And graphically, we can see that as the Fourier's number gets closer and closer to 0, the iterations increases exponentially. With a Fourier's number of 0.001, we get almost 30 iterations to get within negligible error for the code, showing that exact solution is necessary to give us the final temperature needed with these types of problems. The table here shows how that final temperature changes with two different types of Fourier's numbers and how the error changes according to each iteration. And that is our project. Thank you.